Hello everyone, it's a pleasure meeting you all in my mathematics class. Today I'll teach you the first fundamental theorem of isomorphism, which states if G star is a group and G dash delta is another group, and if there is a homomorphism F from G star to G dash delta with a kernel K, then K is normal subgroup of G, and that the quotient group, namely G over K, is isomorphic to f of G. I'll read this theorem. If f is a homomorphism from G star to G dash delta with a kernel K, then K is a normal subgroup of G. This is a normal subgroup of G. Normal subgroup of G, and the quotient group G over K is isomorphic to f of G. So this is the theorem. Here I have drawn the diagram. This is the group G in which the operation is star, and G dash is the group in which the operation is delta, and K is the kernel of F, and which is a subgroup of G. We have to prove that this K is a normal subgroup, and this G over K is called the factor group, which contains the left coset or right cosets, set of left cosets or right cosets. And there is we have to prove that the homomorphism defined by phi from G over K to G dash is isomorphism. That is, we have to prove that the function phi from G over K to f of G is an isomorphism. That is, let us make things certain points very clear. See, here you must understand what is called isomorphism. If it is a homomorphism, it is called a homomorphism if, see, f of A star B is equal to f of A delta f of B. This is the definition of the homomorphism. So if I say that there is a homomorphism from f G to G dash, means f of A star B is equal to f of A delta f of B for all A B belonging to G. And what is the meaning of kernel K? Kernel F. See, what does it mean? See, if I say that K is the kernel F, I have written here, you just see that. K is the kernel of, see, it is the kernel F. I have written here. It is the kernel F. And we say that it is a kernel F. The definition of kernel F, that is, G is a subgroup of G. K is a subgroup, see here, K is a subgroup of G, and K is the kernel of F. It is a subgroup of G. K is a subgroup of G. K is a subgroup of G. But we have to prove that it is a normal subgroup. But before that, we must understand what is kernel F. Kernel F means K is a subgroup of G, and it contains all those elements which is mapped on to the identity element E dash. Here you have got the E dash. E dash belongs to G dash. This is the identity element. And if you take this K, all the elements here in K will be mapped onto E dash only. So K is a subgroup which contains all the elements which are mapped on through F to E dash, and therefore this K is called the kernel F. Now we have to prove that this kernel F is a normal subgroup. So we must know what is the meaning of a normal subgroup. We say that here I have given here, see, here I have given, see, a subgroup H is a normal subgroup if and if only this condition is true. So here I have written, see, a subgroup H of G is a normal subgroup if and if only A inverse star H star A belongs to H for all A belonging to H and H A. That is, for any A you take in H, G. For any A you take in G. And for any H belonging to H, H is a subgroup of G. If this element, namely A inverse star H star A belongs to H, then we say that such a group will be called as a normal subgroup. So this is a. So you must know what is a normal subgroup. What is a kernel first? Know the definition of kernel. Know the definition of normal subgroup. Now let us prove that this K is a normal. That is, the kernel is a normal subgroup. Okay. Now, so this is. Now what I do here is, for any, you consider an element. You consider an element A minus 1 star K star A, where this A is any element in G and A to the power of minus 1 is, that is nothing but the inverse of A. So A to the power of minus 1, if A belongs to G, actually A to the power of minus 1 belongs to G because G is a group. So for any A belonging to G and K belonging to K, you consider the element A minus 1 K star A. Consider that element. And operate U, that is apply F. That means F of A to the power of minus 1 star K star A, which is equal to, because this F is a homomorphism. F is a homomorphism. Because see, F of A star B is equal to F of A star B star C means F of A star F of B, F of A delta F of B delta F of C. So this is how you must understand. So because F is a homomorphism, I can write it as F of A to the power of minus 1 delta F of K delta F of A. But it has been proved. I am not proving it here. But we can prove that F of A to the power of minus 1 is equal to F of A whole to the power of minus 1. Can you see this? See, F of A to the power of minus 1 is equal to F of A whole to the power of minus 1. Therefore, we get this F of A minus 1 delta F of K. This is equal to F of A whole to the power of minus 1 delta F of K delta F of A. Understand that once it comes to G dash, the operation is delta. The operation is delta. That is why we have put delta here. But we know that what is this F of K? F of K, as per the definition of kernel, any element, K is an element in K. See? K is an element in K. And the definition of the kernel says that any element you take in K, it is mapped onto the identity element in G dash. That means here it is mapped down to there. So any element you take in K, it is mapped down to E dash. Therefore, what is the value of this F of K? It is E dash. And identity element is, it leaves the element as it is when operated. That is, E star A is equal to, see, E star A is equal to A star E is equal to A. This is true for all. Whether it is A dash, here A dash is the identity element in G dash. Therefore, here you see that E dash delta of anything is the same element. Therefore, this E dash is the identity element. Therefore, we get F of A to the power of minus 1 into the delta F of A. But you must know that F of A to the power of minus 1, they are inverse of each other. They are inverse. That means A star minus 1 is equal to C. A star A minus 1 is equal to E. And here you see that these two are elements lying in G dash, where the element, that is the identity element is E dash. You see that this f of a whole to the power of minus 1 delta f of a is equal to a dash. So if I can prove that, that means what? F of any element that you have taken, any element you have chosen, that element is equal to e dash means this element must lie in K. Only when this element lies in K, it can be mapped onto E dash. Therefore, this a to the power of minus 1 star K star A is an element of, say, I'll take here, see. Therefore, this a to the power of minus 1 star K star A belongs to here, this one, see. Therefore, this one, see, I have written here. Therefore, a to the power of minus 1 star K star A belongs to A because in K, all the elements in K are mapped onto E dash. Now it is mapped onto E dash. Therefore, this is an element of K. Therefore, see, this means, say, I told you that this condition, it obeys this condition. What is the condition? If H is a subgroup and if it obeys this condition, A minus 1 H star A belongs to H, then H must be a normal subgroup. You can just see that A to the power of minus 1, A is an element of G, K is an element of K. So these elements of K obey the what? The elements obey the rule that A to the power of minus 1 star H star K, A must belong to K. That means K, and therefore it satisfies the definition for a normal subgroup, and therefore K is a normal subgroup. So we have proved that K is a normal subgroup. See, K is a normal subgroup. So I have proved that K is a normal subgroup. So the first part is over. So K is a normal subgroup. I have proved. Now let us take this phi. See, this phi is the mapping from G over K to G dash. How do I define this? Say I define the mapping G over K to G dash as phi of K. That means you take any A, when it comes over here, it is f of A. And for this A, the corresponding element is AK, and this is mapped onto A. That means A is mapped onto f of A, and this phi of AK is mapped onto f of A. So phi of AK, so you take any element. So if you come here, the element G over K will be coset. AK is a coset. So phi of K, AK is equal to f of A for all A belonging to G. Now we have to prove that this is a one-to-one in the sense that it is well defined. If I can prove that it is one-to-one, suppose that if two elements, that is, what I have to prove is that if two elements are equal here, then when you map, they must be equal in G dash also. You take two elements here, AK and BK. If the images are equal, you have to prove that if the pre-images are, this is called, say phi, when you do this mapping phi, this here it is called domain and this is called the codomain. If you map this AK is called the pre-image and f of A is called the image. F of A is called the image, see, f of A is called the image and AK is called the pre-image. So if the pre-images are equal, the images are equal. Or if the images are equal, pre-images are equal. Only when this condition is satisfied, we say that it becomes a fine mapping. How to prove that? See, let us, you take any two elements AK and BK. Let us suppose that they are equal in G over K. We will prove that it is correspondingly this f of A is equal to f of B. AK, it is mapped onto f of A. BK mapped onto f of B. If AK is equal to BK, then the corresponding elements f of A is equal to f of B. So that is what we should prove. Now let us see. See, you take any two elements AK. Let us, for any AB belonging to, you consider AK and BK. Let us suppose that the AK is equal to BK. But AK is equal to BK, then you apply this A minus 1 on both sides. You apply this A minus, and you must know that this star is there. A star K, B star K, everything, star is understood. So you apply this A minus 1 on both sides. So it is A minus 1 star A K. Right hand side also A minus 1 star B K. But A minus 1 star, they are elements in A and A minus 1 are reciprocal of each other. And A minus 1 star A is equal to A. Therefore, E star K is equal to A minus 1 of BK. A to the power of minus 1 star BK. That is, A to the power of minus 1 star BK is equal to K. So, A to the power of minus 1 star BK is equal to K. This simply implies that A minus 1 star A to the power of minus 1 star B must be an element of K. Must be an element of K. A to the power of minus 1 star BK is equal to K. This implies that A minus 1 star B is equal to K. So what is that we have proved now? If AK is equal to BK, then A to the power of minus 1 star B must be an element of K. But what is K? K is nothing but your kernel. K is nothing but your kernel. So if you apply F on this A minus 1 star B, understand that if AK is equal to BK, we are able to prove that this A minus 1 star B is an element of K. But what is K? K is the kernel of F. What is the meaning of kernel of F? If you operate that F on the elements of K, it must be mapped onto E dash, which is the identity element of G dash. Okay. So what is that I have written here? See, I have proved here. So this implies that A minus 1, see, A minus 1 star B belongs to K, and therefore F of A minus 1 of B must be equal to E dash. See, I have written here. See, that is nothing but F of A minus 1 of this, F of A minus 1 delta F of B, this is F of A whole to the power of minus 1 delta F of B, which is equal to, so you must know that this must be mapped out, so this element must be equal to E dash. This must be equal to E dash. You must know that this must be mapped onto E dash, because if it is an element of K, it is mapped onto E dash only. Therefore, this F of A minus 1 of B is definitely mapped onto E dash. When that is so, you are getting F of A to the F of A whole to the power of minus 1 delta F of B is equal to A dash. Now you operate F of A on both sides. F of A delta F of A to the power of minus 1 delta F of B is equal to left multiplication. F of A delta E dash. But F of A delta F of A minus 1 is nothing but your E dash. Nothing but. So E dash, see, you are getting, see, that is E dash of F of B. I have not written that step. This is nothing but your E dash. So this is your E dash. This is your E dash. So E dash of delta F of B is equal to F of A of the F of A delta E dash. Therefore, you get from this implies that F of A is equal to F of B. So what is that I have done here? If I take here two elements, AK is equal to BK, then correspondingly you will find that corresponding to this is the F of A, and corresponding to this F of B. So we are able to prove that if the pre-images are equal, images are equal, and therefore here it is 1 to 1. See, it is well defined, and and AK is going to be phi is a 1 to 1 mapping. That means prove that phi is a homomorphism. What is that? Phi is a homomorphism. What is that? Now let us take. So this we have proved that. Let us come to this. Now you take two elements here. F of AK. That means, what is the meaning of homomorphism? Homomorphism means phi of AK star BK. You must be able to prove that this is equal to phi of AK delta phi of BK. So this is homomorphism. So let us prove that. So what is your phi of AK star bk, because ak and bk are elements in G over k. G over k is the quotient group. So phi of ak star bk is equal to phi. So this ak star bk can be written as a star b of k. So I have written here a star b of k. Phi of a star. Suppose you call this as your single letter. Suppose that you call this as your x. See what is letter? Suppose it is x. So it is nothing but your phi of. See, it is just like your phi of ak, which is equal to f of a. By definition, phi of ak is equal to f of a. So that is why I have written here phi of xk means it must be equal to f of x. It must be equal to f of x by the definition. See, here I have written what is my definition here. See, here is the definition. This is the definition of the mapping phi. So applying that, we are able to get here phi of f of a star b. But f of a star b, it can be written because this can be written by this. Say f of a star b is equal to f of a delta f of b. Therefore, I can write this as, say, f of a delta f of b. But f of a is nothing but what? Phi of ak by definition. Delta f of b means, so I am able to prove phi of bk. So phi of ak star bk is equal to phi of a star b of k. But by this definition, by the definition of this phi, we can write this as f of a star b. But f of a star b, because f is a homomorphism, f of a delta f of b, that f of a is equal to phi of ak delta phi of bk, and therefore phi is a homomorphism. So I am able to prove that phi is a one-to-one mapping in the sense that it is a well-defined mapping. By the way, it's also bijective mapping, and phi is a homomorphism. And let us prove that. See, next let us prove that it is a one-to-one. That is in the onto mapping. Onto mapping means for every element you must be able to get one element. That is, for every image there is a pre-image. For every image there is a pre-image. If I can prove that it is a onto mapping, so already it is one-to-one. If I can prove that it is onto, then it becomes a bijective mapping. That is, it's a bijective mapping. It's a bijective. It is a one, that it is one-to-one, and onto means it becomes a bijective mapping. If it becomes a bijective mapping, then f is nothing but an isomorphism. So if you want to prove that phi is an isomorphism, prove that phi is a one-to-one mapping and an onto mapping. It is one-to-one because I am able to prove that it is a one-to-one. And let us now prove that it is an onto mapping. Let us prove that it is an onto. Onto means what? For every element in G dash, you must be able to get an element in G over K. If that is true, then we can say that phi is also an onto mapping. Already I have proved that it is a one-to-one mapping. So it's one-to-one. If I can prove this onto, then it becomes a bijective mapping. If it is a bijective mapping, this phi becomes an isomorphism. Okay. Now, so you see that I take, let phi of k, a, k you have written here. See? Here, let x belong to G dash. So you take any element belonging to G dash. You take any element belonging to, if for every element there must be an element. See, if let x belong to, f is a homomorphism. Therefore, so you see that if you take any element x here, then there must be f is a homomorphism. F is a homomorphism. Therefore, there exists an element a in G such that f of a is equal to x. Such that f of a is equal to, that's what I have written. See, let x belong to G dash. F is a homomorphism implies that there exists an a belonging to G such that f of a is equal to x. That because f is a homomorphism. And since that means f of, but what is our f of a? F of a is nothing but phi of ak. Therefore, phi of ak is equal to f of a is equal to x. That means I may for any x, see here, for any x I am able to get only ak. You able to catch what I am telling you? So you see that what I have proved here is that my argument is you take any x here, a corresponding element exists here because it's a homomorphism. We have to say that it is a homomorphism. So it is for any element x, there exists one a such that f of a is equal to x. But for this a, there is a, for this f of a means, say f of a, but f of a, by definition of this phi, there exists this, f of a must be equal to phi of ak. For corresponding to a, there is one quantity, namely ak. So for this, phi of ak is equal to f of a. That is what I have written here. Phi of ak is equal to f of a is equal to x. That means it is a onto mapping. That means for any x, for any a here, for any f of a, corresponding ak is present in the quotient group, and therefore it is an onto mapping. See, I have written here. So this is a onto mapping here. So this is, so I have written here. This is this is onto mapping. See, therefore phi is onto. So here I have written here. See, this is onto. So phi is onto mapping. Now you see that phi is onto, phi is 1 1, phi is onto. So I am able to prove that phi is a 1-to-1 mapping and also an onto mapping. Because of this, phi is an isomorphism. So what I have proved here is that phi is a, phi from g over k to g dash is an isomorphism. So